So today we will discuss about the nuclear physics. We will talk about the isotopes and what are the principles that we have to keep in mind during nuclear when we write a nuclear equation. What is the mass defect or mass energy equivalence? And then we will talk about fission and fusion as the reaction. Before we start working with all those concepts that I said at the beginning of beginning of the video, let's see what is the symbol that is used for an atom. So any atom, this is the symbol that can be represent any atom, carbon, oxygen, anyone. And then, so this will be representing the symbol of the atom. And then we will have a Z number here and an A number here. So if X represents the symbol of the element on the periodic table, Z will represent the number of protons. And A will represent the number of protons and neutrons, which is known as atomic mass number. Atomic mass number. So atomic mass number is the number of protons and the number of neutrons. And in a more general name, those are known as the number of nucleons, because they are in the nucleus. So if we have an element, let's say tungsten, so tungsten is W74-186. That means that we have, as the number of protons is 74, and the number of neutrons will be 186 minus 74 equals to 112 neutrons. But as a total number of nucleons, we have 186 as the total number of nucleons into this particular element. Now, one thing that we have to keep in mind is that when we see that an element in the periodic table, then the number of protons in that form of isotopes of the element is always the same. So when we are saying that we have, let's say carbon 6 and 12, and carbon 6 and 14. In other words, this is known as carbon 12 and carbon 14. Two forms of isotopes of carbon. Carbon 12 is most common, but carbon 14 as well is quite common in the form of this element. Now, those two are known as the isotopes. You probably have heard this and have seen this in chemistry. So when we are talking about isotopes have, which are different forms of the same element in the periodic table. So isotopes have same number of protons, because protons are the one that define what is the element, and then different numbers of neutrons. within the nucleus. So on this case, which we discussed, carbon-12 has the number of protons is equal to 6, while the number of neutrons will be 12 minus 6 equals to 6. But when we are discussing and talking about carbon-14, the number of protons will be 6 because we are talking about carbon, and the number of neutrons will be 14 minus 6, which is equals to 8. Okay, so in general, the term nucleon refer to both the protons and neutrons, and the atomic mass is the total number of nucleons. So if we have, let's suppose, an element, let's say oxygen 16, that means that the oxygen being on the 8th place on the periodic table, the number of protons will be equals to 8, while the number of neutrons will be 16 minus 8 equals to 8. However, the number of nucleons is 16. And when we have, let's say, tin 122, then tin is on the 50th place on the periodic table. So as the atomic way to write it will be 50,122. So that means that the number of protons is equal to 50, while the number of neutrons is equal 122 minus 50 equal to 72 neutrons. And when we have an atom of tin, then we as well have the number of electrons is the same as the number of protons, because atom is a neutral entity. Okay. So the interaction, the nuclear interactions are represented by those that are known as the nuclear equations. Nuclear equations. Nuclear interactions can involve the disintegration of the nucleus, meaning that new elements will be created. The transmutation of nuclear and a host of other interactions, which will be, we will see it especially when we see fission and fusion. However, in the nuclear equation, the original isotopes are often referred as the parent isotopes. And when the final, and then after the reaction, the final isotope is known as the daughter isotope. So when we're writing a nuclear equation, it is important to have two principles. That is known as a conservation of charges, and the other one is conservation of masses. Okay, which is translated into conservation of number of nucleons. So in other words, what we are saying here is that the sum of atomic number, the sum of atomic number on the parent side of the equation right, is equal to the sum of atomic number on the daughter side of the equation. On and then the sum of atomic mass on parent side is equal to the sum of atomic mass on the daughter side. Of the nuclear reaction. So let's suppose that we have an example here. When a boron-10 nucleus capture a neutron, a new element and an alpha particle are produced. What is the new element? Okay, so now we have boron, so boron-10 plus a neutron is producing a known element plus alpha particle, which is helium-24. So every time that you see an alpha particle, it's either alpha particle or helium-24. Good. Now, when we take a look at first of all, this side here is known as parent side. And whatever is produced on the other side, it's known as the daughter side. Okay, so now we have, let's apply, first of all, a conservation law of masses. Conservation law of masses. After we write the equation. Let's write the equation first. So the equation will be a neutron, which is captured by a boron, which is on the 5th place on the periodic table, and it is boron-10 form of isotope of it, will produce an unknown element with a certain number of atomic number and a certain atomic mass and an alpha particle, helium-24. Great. So now let's apply the conservation law of masses. Conservation law of masses is saying the mass, the sum of the mass on parent side of the equation will be equal to the sum of the mass on the daughter side. So this mass here plus this one here should be equal to this A plus 4. So the conservation law of masses will be 1 plus 10 equal to A plus 4. And from here, we find that A is equal to 7. Okay, so now we know that the atomic mass of this unknown element is 7. In other words, we know the number of nucleons on this particular unknown element. Now let's apply the conservation law of charges, which is saying that the sum of the charges in parent is equal to the sum of the charges on, or the sum of the charges on the parent side of the atomic sum of the atomic number in the parent side is equal to sum of the atomic number in the daughter side. So now when we are talking about the atomic number on the parent side, what we are saying what is 0 plus 5. And when we are talking about the atomic number on the daughter side, then we say Z plus 2. So the conservation law of charges, or the conservation law of atomic number, is 0 plus 5 is equal to Z plus 2. And from here, we find that Z is equal to 3. And if you refer to periodic table in your data booklet, at number 3, what is lithium. So now we have a lithium that has an atomic number of 3, and it is an atomic mass of 7, which is the same as saying we are dealing with the lithium 7 form of isotope of the of this element. Okay, so this is what we do when we are figuring out what is the, or how can we find the unknown element. Okay, so let's move now to that is known as the mass defect and mass energy equivalence. So mass defect and mass energy equivalence. All right, so when we were working with proton and electron and all that other particles in the previous up to now, we said that the mass of a proton is 1.67 times 10 to the power of negative 27 kilogram. And this is from your periodic table. So from your data booklet, sorry, from your data book. But when we are talking now, so this is good to use when we have proton and electron. That information that you have there is good to use when we have proton and electron into very not as much accuracy is not needed. However, when we are talking in the context of nuclear masses and energy, we need to be more precise. We'll bring the table here and then we will talk. So as you see here, even the charges, when we are adding more digits after the decimal point, are not longer 1.60 times 10 to the power of negative 19, but we have a more precise value of the charges. But let's move to the mass of the electron, the mass of proton, or the mass of neutron. So when we see the mass of the electron as you are entering or adding more digits after the decimal point, which means that you are making it more precise, then it's different from that formula that you have, or that information that you have on the periodic, on the data booklet as 9.11 times 10 to the power of negative 31, which is fine to use when we are not dealing with the nuclear, okay, and the energy that the interaction between particles is experienced. Okay, so or when we talk about the mass of proton, we say mass of proton and mass of neutron is 1.67, but actually they are a bit different. Now, in order to make it more comprehensible, what we are presenting is that is known as the unified atomic mass. So this one here is the unified atomic mass, which is the exact value of it, or the ratio that is used to evaluate it is 1.660539 times 10 to the power of negative 27 kilograms. So it is nothing but 1/12 of mass of the carbon-12 nucleus. Okay, and so on this way, what we are doing is we are saying, we are comprehending exactly what is the mass of the proton as 1.0072, and so, and what is the mass of a neutron, 1.008665, and the unified mass, and then the mass of the electron is 5.485 times 10 to the power of negative 4 mass of the unified mass times unified. So this is the same as saying times U times U times U. So there are two ways so that you will see the on the questions, the mass of the proton, electron, or a neutron in terms of the kilogram, those ones here, or sometimes you will see it in terms of the unified mass. So when we are dealing with the electron, is this what we will refer to? Proton is this one here, and a neutron is this one here. So after scientists discovered that the nucleus contained protons and electrons, they were capable to calculate the theoretical mass of a particular isotope by adding number of protons and number of electrons. So what we are saying here is, let's say that we are dealing with helium. So helium-4, within the nucleus of helium, we have the number of protons is equal to 2. The number of neutrons will be 4 minus 2, which is equal to 2. So if we have 2 protons and 2 electrons as not connected into the nucleus of the helium, then we will see that the mass as those 4 particles, 2 protons and 2 neutrons, are separate, are together, so but not connected, not binded into the nucleus of helium, but as 4 separate particles, 2 protons and 2 neutrons, not binded together into the nucleus, will be mass, let's say, call it theoretical, will be 2 times mass of the proton plus 2 times mass of neutrons. And now using the information that we have here, either the unified mass or not, let's use the unified mass, 1.0072. 7276 times U plus 2 times 1.008665 times U will be the theoretical mass of those 4 particles that actually form the nucleus of helium, but we are considering them as separate entities, will be 4.03182 times the unified mass. However, using mass spectrometer, the measured mass of the, in this case, helium-4 is slightly less. So mass of helium-4 was actually 4.00260 times unified mass. And this difference between the particles, protons and neutrons, separated as the exact numbers of protons and neutrons that form the nucleus, but not bind it into a nucleus, the difference between the theoretical and the measured, it's known as the mass defect. Mass defect. Okay? And then Einstein, as genius as he was, he said that, okay, and he provided and demonstrated theoretically that mass and energy are interconnected between each other. So he said that the energy is the mass defect times c squared. And notice here that the change of mass should be in kilograms, not in unified atomic mass. So this equation shows that certain amount of energy has an equivalent mass, and certain amount of mass has equivalent energy. This is known as the mass energy principle. Okay. So certain amount of mass is energy, has equivalent energy, and certain amount of energy has equivalent mass. Let's see an example where we are calculating that equivalent mass. A nuclear reaction produces an energy of 9.0 times 10 to the power of 11 joules. Okay, and now let's figure out what is that equivalent mass of this energy. So now, based on the equation that mass is energy is mc squared, then mass will be energy over c squared, and in our case will be 9.0 times 10 to the power of 11 joules over c, which is the speed of light. And we consider it to be a constant value. So now the mass, the equivalent mass of this energy is 1.0 times 10 to the power of -5 kilograms. Interesting. Based on this idea of mass energy equivalence, physicists interpreted or explained the mass defect as the binding energy that holds protons and neutrons together. We talked about binding energy when we talked about photoelectric effect, that the electrons were removed from the original structure to overcome, and that work function is known as the to overcome the binding energy that it is keeping the electron together. So the binding energy exists even between protons and neutrons to keep them together. So due to the large repulsive electrostatic forces between protons, a large amount of forces are required to hold the nucleus together. And we know that nucleus is a very stable structure. The binding energy resulting from what is called later strong nuclear forces, is equivalent to the mass defect using the Einstein's equation. So let's see an example. A mass of one nucleus of potassium-40 was measured. I will bring the question here. Was measured, and it was 3 point whatever on the situation. So when you see that the mass of an element is given to a high number of digits after the decimal point, not 2, not 1, not 2, but 4, 5, then what the clue for you has to be that you are using the mass defect. Okay, so what we are looking for here is what is the mass defect of the binding energy of potassium. Okay, so let's figure out what is that we call theoretical mass, which is nothing but the number of mass of all protons and all neutrons that are in the nucleus of potassium-40. So potassium-40, which is, one second, in what place is potassium? Yeah, if you refer to the periodic table, you will see that potassium is on the 19th place, okay? On the, not like this, not like this. Potassium is on the 19th place, so 19th. And now we have that form of isotope that is potassium-40. Okay, so from here we find that the number of protons for potassium is 19, and the number of neutrons is equal to whatever is 40 minus 19 equals to 21. So now, when we are calculating the mass, theoretical mass of potassium, then we will go whatever is the number of protons times 1.007276 times unified mass plus the number of neutrons, so that in our case is 21, but let's write it as a generic one, times 1.00866 times atomic mass. And since in our case the number of protons is 19 times 1.00726 times U plus 21 times 1.008665 times U will be equals to 40.320209 times U. So this is the theoretical mass. Now, the mass defect will be whatever is the theoretical mass minus measured mass. We know, or we calculated, that theoretical mass is 40.320209 times U minus, given in our question was that theoretical mass was 39.96, so 39.9687 U. Then the mass defect in terms of the unified mass will be 0.351501 times U. When we convert this into kilograms, then, so this is into unified mass, in terms of the unified mass, and when we convert it into kilograms, we'll be multiplying it by the unified mass, 1.6606 5.4 times 10 to the power of negative 27, and this will be 5.83695 times 10 to the power of negative 28 kilograms. And this will be in terms of the kilograms. And always when you are using the energy formula, you will convert it into kilograms. Now, the binding energy is mass defects times c squared, so it will be a 5.83695 times 10 to the negative 28 times 3.0 times 10 to the power of 8, the whole thing to the power of 2. So the energy will be 5.253 times 10 to the power of negative 11 joules. This will be in joules. And if we want to convert it into electron volts, then the energy will be 5.253 times 10 to the power of negative 11 times 1.60, no, divide by 1.60 times 10 to the power of negative 19, and the energy, binding energy in electron volts or mega electron volts will be 328.3 mega electron volts, and this will be the binding energy for potassium 40. Okay. I think that I will close it here and then have fission and fusion in a separate video because it's a bit too much now, and then we'll do that in a separate video.